Next, we will solve one of the important question. Okay, that's an important one. Given a random sample of a size n from uniform 0, theta distribution, construct most powerful test for testing h naught theta equal to theta naught versus h1 theta equal to theta 1. Here theta 1 is greater than theta naught. Okay, so this is a question. So we have to construct MP test for testing h naught versus h1, right? Here it's given that theta 1 is greater than theta naught, right? And what is the f of x theta? It is a density of uniform 0, theta distribution. It is 1 by theta, right? If 0 less than x less than theta, right? So under h naught, f of x theta naught equal to 1 by theta naught, right? Under h1, f of x theta 1 equal to 1 by theta 1, right? But here in this case, is a sample of size n, right? So we have to take the likelihood, right? Then under h naught, likelihood theta naught x1 x2 so on xn equal to, what is that, product of f of x theta, right? That is a product of 1 by theta, right? That means it is equal to 1 by theta naught power n, right? 0 less than here x or xn, it is xn, right? This is less than theta naught, and 0 otherwise, right? Then under h1, likelihood is l theta 1 x1 x2 so on xn equal to 1 by theta 1 power n if 0 less than xn less than theta 1, 0 otherwise, right? So from the Neyman-Pearson lemma, we know that we reject h naught for the large ratio, right? Then we have to take the ratio of likelihood under h1 and likelihood under h naught. But here in this case, the ranges are changes, right? In under null hypothesis, the range is 0 less than xn less than theta naught, right? But here in h1, 0 less than xn less than theta 1. We know that theta 1 is greater than theta naught, right? It's given in the question. So we have to rearrange these likelihood function. Okay, that is under h naught, likelihood theta naught x1 x2 so on xn equal to 1 by theta naught power n if 0 less than x less than theta naught, right? Then if theta naught less than x less than theta 1, take this type. Okay, here we have to split these down. We know that theta naught is less than theta 1, right? So we can write this type also. This implies 0 less than x less than theta naught less than theta 1, right? This term. Then we have to split this term and we can write this type. Okay, if theta naught is less than x less than theta 1 under null hypothesis, then that is 0, right? 0 otherwise. Then under h1, likelihood is equal to 1 by theta 1 power n if 0 less than x n less than, here xn, right? xn less than theta naught, and if 0 theta naught less than xn less than theta 1 1 by theta 1 power n, right? The same term here we split the range, right? Then you can write 1 by theta n if 0 less than x n less than theta naught, 1 by theta 1 power n if theta naught less than x n less than theta 1, then 0 otherwise. Okay, then we have to take the ratio, right? That is likelihood under h1 divided by likelihood under h0, right? Which is equal to, first we will write the ranges, right? If 0 less than x n less than theta naught, if theta naught less than x n less than theta 1 otherwise. Okay, here we have to divide these by these, right? Then you can get theta naught divided by theta 1 power n, and here next 1 by theta 1 power n divided by 0, which is equal to infinite, right? Then 0 otherwise. So we reject h naught for the large ratio, right? Here we get one rejection region, that is theta naught less than xn less than theta 1, right? Because it is a infinite, it's a maximum value, right? The large ratio, right? But here we need to find for in this range what is the maximum, right? For that we have to draw a graph. Here this is a range of xn, here a likelihood under h1 divided by likelihood under h0, okay, and here theta naught divided by theta 1 power n infinite. So we know that 0 to theta is take the value theta naught by theta 1 power n, right? This value. Then theta naught to theta 1 which takes the value infinite, right? So here one of the rejection region is theta naught less than, this is the rejection region, right? Theta naught less than xn less than theta naught theta 1 is a one of the rejection region. But here what is the rejection region then? It's a constant, right? So here we will take the first sum value is a k star, and here also the last sum maximum value is a k. It's a constant, but we have to take two k values. Okay, here first one is k star and second one is a k. Then we can get here three rejection regions, right? Here 0 less than xn less than k star, and also here k less than xn less than theta naught is a rejection region. And here theta naught less than xn less than theta 1 is also a rejection region, right? Then we will write the test function as a test function for testing h0 versus h1 is phi of x or xn, right? Xn equal to 1 if, here we will consider first this case, okay, this one and this one, that is if k less than xn less than theta naught or theta naught less than xn less than theta 1, okay, theta 1 0 otherwise. Here one more value, right? That is one more rejection region, right, based on k star. So we will write another function also, that is we will take as a phi star of xn, okay. phi star of xn, 1 if 0 less than xn less than k star, or theta naught less than xn less than theta 1, 0 otherwise. Okay, so in this case we will get two test function in the case of uniform 0 comma theta. Okay, this is important, so we have to remember this. Then we want to obtain that size and power, right? Okay, first we will take this test function, then obtain size and power. Then after we will take this test function, that is phi star of xn, then we will obtain the size and power of the test. Okay, here first we consider